All right, who's got a question? Annie.
I was just confused for one of the problems. I can pull it up. I can get in there, but it was one of the which one's the oxidizing agent, reducing agent in the grams, and like I can understand that, but when in the reaction, the thing that was reduced got reduced by 3, and then the thing that got oxidized by 2. Why are the numbers not the same?
So let's look at an example.
I can pull up the problem.
If you want to pull up the problem, we can do that problem, or we can look at it in a different way.
Yeah, I did that. I was just confused also.
So let's do a simple one, because I think I know what the problem is. But
Did I do something wrong? Is that what you're telling me?
no, you just haven't finished thinking about it yet. So if we have this equation, so this is a redox reaction, and so to figure out what's going on, we're going to assign the oxidation numbers. So this one is relatively straightforward to assign because we only have ions and neutral atoms. So what's the oxidation number for neutral chromium? 0. What's the oxidation number for nickel 2+? 2+, the charge on the ion. What's the oxidation number for chromium 3+? +3. So anytime we have an ion, the charge on the ion is the oxidation number. What's the oxidation number for neutral nickel? 0. So anything in its neutral elemental form, whether it's a neutral metal or something like O2 or H2 in its neutral elemental form, just that element all by itself, its oxidation number is going to be 0. So let's look at what's going on here. Is chromium gaining or losing electrons? How many? Okay, so I'm going to say each chromium loses 3 electrons. Now, if we look at the nickel, what's happening to the nickel? Is nickel gaining or losing? Gaining. And how many does each nickel gain? 2 electrons. So we're going from 2+ to neutral, so we're gaining 2 electrons. And so you might look at this and say, they're not equal. This is a problem. It is not the case that each atom has to gain or lose the same number of electrons. It's that the total number of electrons gained has to equal the total number lost. So how many chromiums do I have involved in this reaction? 2. So I have 2 chromiums, and each chromium is losing 3 electrons. So that's 6 electrons lost total. How many nickels do I have?
3, I see.
I have 3 nickels, and each one is gaining 2 electrons, so that's 6 electrons gained. So I'm guessing that in the problem that you're looking at,
It's the exact same.
you have not taken into account the stoichiometric coefficients, or like sometimes if you have something like this where you've got like that's not a good example. Let's do. That's not going to be a good example either because that doesn't exist. I hate these examples that don't exist. Let me find something different. Okay, so let's say we have iron nitrate as one of our reactants. And let's imagine that it's the nitrogen that's going to be changing. Right? Even if we have a coefficient out here of 1, how many nitrogens are going to be changing no matter what we do? 2. Right? So we have to take into account any subscripts and any coefficients to count up the total number of atoms that are either gaining or losing.
I think I'm still confused on
So why don't you tell me what the reaction is?
It's.
Or do you want to give it to me and I can copy it
Yeah.
down?
Then I don't have to read it all.
So it's this one,
No,
whatever.
sorry.
This one?
Yep.
Okay. So we've got 2 gold plus 2 BRF3 plus 2 KF goes to BR2 plus 2 KAUF4. Okay. So let's run through this. What is let's make sure that it is balanced for mass. So 2 golds, 2 bromines, 6 fluorines, no, 8 fluorines, 8 fluorines, 2 potassiums. Okay, we're good. I just want to make sure that it didn't get copied down wrong or something.
Oh, yeah.
Okay, what's the oxidation number of gold when it's all by itself and it's neutral? 0. What's the oxidation number of fluorine? -1. Fluorine's always -1. So if fluorine is -1 and there are 3 of them, what's the total contribution from the fluorines? -3, and I like to write the total contribution underneath. This is an overall neutral compound. So if the fluorines contribute -3, what must the bromine contribute? +3. And there's only 1 bromine, so that means that this +3 has to be carried by that 1 bromine all by itself, so that means the bromine has an oxidation number of +3. Notice that we did not, in order to assign oxidation numbers, it doesn't matter what the coefficient out front is, we just ignore that. All right, what's fluorine? -1, and what's potassium? +1. So this is an ionic compound, so if you looked at that and said, oh, I know those are ions, you could assign them just based on knowing what their charges are. What's bromine in this form, Br2? 0. So this is an example of an element. It's all by itself. It's not bound to any other kind of element. It's neutral, and so its oxidation number is 0. What's fluorine? -1. What's potassium? +1. This is an ionic compound. So if we have 4 fluorines, they contribute a total of what? -4. The potassium contributes a +1. There's only 1 of them. This is overall neutral, so what must the gold contribute?
I was thinking that since there's 2 a coefficient, I put that in.
Right.
So I only had it being at 2 because I figured it's. Yeah.
Right, so when we're assigning oxidation numbers, we ignore the coefficients. Because what you want to think about is if I just gave you a formula, any formula for a compound, and I said assign the oxidation numbers, the rules would allow you to assign the oxidation numbers without that compound being part of a reaction. So the coefficients are just going to tell us how many of this molecule are involved. But we can assign the oxidation numbers completely independent of how many.
I have a question on the harder one.
Okay, let's finish going through this one because I'm guessing it would be useful. Yes, we finish this one? All right, so what's changing? Is fluorine changing? No, fluorine is -1 everywhere, so that's not contributing. Is potassium changing? No. So potassium and fluorine are unchanged. They're neither gaining nor losing electrons in this case. So what about gold? Is gold doing something? Okay, so gold is going from 0 to +3. Is it gaining or losing electrons? Losing. So if its oxidation numbers become more positive, that means it has lost negative electrons. So lose. And how many does each gold atom lose? 3. So each gold loses 3 electrons. So if we found something that lost electrons, it means we must have found something that will gain electrons. What's gaining electrons in this case? Bromine. So bromine is going from +3 +3 to 0, is it gaining or losing? Gaining. So each bromine gains, and how many does each bromine gain? 3. And when you're looking at that, you don't worry about how many bromines there are. You're just looking at the +3 and the 0, because this 0 applies to each of the bromines that are in this molecule. Each one has an oxidation number of 0. So we're saying, I don't care how many there are, all I know is each one goes from +3 to 0, and if you go to, in order to go from +3 to 0, you have to be adding negative charges, so we must be gaining, okay? So, how many total electrons are lost? We know that each gold loses 3, but how many total are lost? 6, because we've got 2 golds. So we've got 2 gold atoms times 3 electrons per gold equals 6 electrons lost. And if we were counting these in moles, if we were counting 2 moles of gold atoms, then we would have 6 moles of electrons lost. So we can do it either at the atom level or at the level of counting in moles. Just like we can count it in dozens. Like we could say we've got a dozen gold atoms and they're going to lose 6 dozen electrons. So it's just scaling up and down. How many bromine atoms do we have? We have 2. So 2 because we've got 2 of this whole thing. Each one has 1 bromine. And in the product, we also have 2. One of the things that sometimes can happen is people will say, well, there's 4, because there's 2 on this side and 2 on this side. But remember that these bromine atoms are the same bromines, right? It's just that they start off in this form, and then after the reaction is done, then they're in this form. We don't have 4 total bromines, we have 2. They just change form from reactants to products. So we've got 2 bromine atoms, and each one gains 3, so we're going to get 6 electrons gained. So what is reduced in this reaction? Okay, so gaining is reduction, so this is reduced. Br is reduced, and that means that gold is oxidized. What's the oxidizing agent? Bromine. And often we will say this compound that had the bromine in it to begin with, that's the oxidizing agent, that's the thing we pulled off the shelf and said, let's throw that in because it's going to cause the gold to be oxidized. But it's really the bromine in the compound that's doing it. That makes sense. What's the reducing agent? Gold. So gold, we're throwing gold in to cause bromine to be reduced.
So on an exam, are you gonna want that whole compound or just the bromine?
Either way, I'll take either one. I'll take either one. Okay. Was there somebody wanted a harder one? You have one that was more complicated here. It's probably easier if I just write it down. I think this is one that's on homework. Okay. All right. So let's start assigning. What's oxygen? -2. there are a few examples of cases where oxygen is not -2, but you won't see them. So just so you're aware that it's possible for oxygen to have something other than -2, it's just you won't see. Now, I answered a question on Piazza about this one because the question was, I don't have enough information to figure out what the manganese and the sulfur are, right? So here's what we have to do, we have to take a step back. What kind of compound is this? It's ionic. How do you know it's ionic? And a metal and some nonmetals, right? Do you recognize that unit, SO4? What is that? Sulfate. I'm like, I don't think I heard that. It was all like all at the same time. My ears aren't processing. Okay, so this really is SO4 2 minus, right? So if we know that the oxygen is -2, that means that the oxygen is -8, the total contribution within just the sulfate part from oxygen is -8. So what must the contribution from sulfur be just in the sulfate part? Well, remember that it's got a 2 minus charge,
So
plus 6. That makes sense? Is this too small? Do you want me to rewrite it? William?
I'm just wondering, because the oxygen rule is one of the very last rules that you said hierarchical. So I'm just confused why we would apply that rule first, even though SO.
Because none of the other rules apply.
Okay.
Like, so I know that, so I skipped down that far. Right, so one of the rules that comes before that is that everything has to add up to the charge on the molecule, but we can't use that until we know at least 2 out of the 3 atoms.
So is there not a rule for SO4 just being 2 minus because it already has
Well,
a charge?
Well, so SO4 being 2 minus, that by itself isn't the oxidation state, right? So 2 minus is the charge on the whole molecule. We can use this, because we know that this one is what its charge is, to determine what the oxidation state of sulfur is. But there's no rule so the rule that would apply here would be the sum of the oxidation numbers of oxygen and sulfur have to add up to -2. Okay? Questions about that?
Does that, so when the compound inside it has to like go out, is it only with polyatomic ions?
Are you asking when it has
Like when you have to like make that cancel out with the charge of the sulfur, like how you?
It's with anything that has a charge. So any molecule that has a charge, the oxidation numbers have to add up to the charge on the molecule. Hold that question, because I think it might make sense once we do the whole compound.
I get that part, but I meant just like with the sulfate, like how you have to make the sulfur and oxygen cancel out.
Yes.
Okay.
So anything that's charged, which will include polyatomic ions, will have to do that.
Where did you get the +6 again on the sulfur?
Yeah, so let's do this down here, it's a little bigger. So we know, so if we just did sulfate, right, forget this whole big long thing that looks intimidating. Like if I just said, here's sulfate, let's assign its oxidation number, shall we? This feels a little more tractable, right? So what's the oxidation number of sulfur? Wait, sorry, of oxygen? -2. And there is a total of 4 of them, so that total contribution is going to be -8. Find that? We know that the charge on sulfate is -2. So whatever is down here has to add up to -2. So what must the sulfur be? +6. And since there's only one sulfur, that means that single sulfur atom has to carry the full +6. Does that answer the question of where the +6 came from? Okay. So now I know oxygen here, which is -2, and I know the sulfur, which is +6. And I can put the -8 down here and the +6 down here. This is an overall neutral compound, right? And I can get the manganese in one of 2 ways. I can add these up. What does manganese have to be? +2. The other thing I could have done is said, look, I know if sulfate is -2, this must be a manganese 2+ ion, right? Because this is an ionic compound. If the sulfate is -2, the manganese must be +2. And if it's an ion, then the charge on the ion is the oxidation number. Okay? All right, so we've got one down, that's good. All right, let's do the next one. So, what kind of compound is this?
Ionic,
How do you know it's ionic?
metals and non-metals.
Metal with nonmetals. So that's even though you haven't seen a bismuth polyatomic ion, it's clearly got to be an ionic compound because it's got a metal and a bunch of nonmetals in it. So what's oxygen going to be? -2. And what is sodium when it's an ion? +1. So if I put the -2, if I take the fact that there are 3 oxygens, that's a total of -6 that comes from the oxygens. I've got a total of +1 because there's only one sodium. So what does my bismuth need to be? +5. There's only one of them, so that one bismuth carries the full +5.
What is a bismuth?
What is it? That's Bi is bismuth. It's just the name of the compound.
I just didn't know what bismuth was.
Yeah, it's just an element. I mean, yeah, it's not a compound, it's an element. Let me stop and see if there's questions about this.
How come you don't do anything with the number in front?
Because assigning the oxidation number is a feature of the compound itself. So I could give you 20 compounds and say assign the oxidation numbers of these, and you have no idea if they're participating in a reaction or not. The oxidation numbers are a feature of how the electrons are distributed in the compound, not how many compounds you have.
So then you would use a number when you do, like, go through it?
We will
When
use
you
the
do
numbers
that,
when we
okay.
get to this stage.
Perfect.
Yep. Yeah. Okay, let's do H2SO4. One way to do this is to recognize, oh look, this has a sulfate in it. I know what sulfate does. Sulfate looks like this. It's -2 and +6. And what is hydrogen? +1. And so I can double check that that all adds up. This is -8 +6 +2. Does that make it overall neutral? That's good. All right. What kind of compound is this? Ionic or molecular? Ionic. Why do you think it's ionic? Because it's got sodium in it. It's got a manganese. The manganese is another metal, but it's got a non-metal, right? So this is going to be ionic. This is a polyatomic ion that you haven't learned. It's called permanganate. You don't need to know its name, but it's a polyatomic ion. What is the charge on sodium when it is in an ionic compound? +1. So that means this whole thing, NNO4, must have a 1- charge. You don't have to know that to solve the problem, but what's oxygen? -2. So that means oxygen is a total of -8. Sodium brings +1. What does the manganese need to be? +7. And there's only one of them, so the full +7 rides on the manganese. All right. Look what we have here. What is this? This is a sulfate. We've got 3 of them, but the oxidation numbers of sulfate are always -2 and +6. But to figure out what bismuth is here, we have to take into account how many total oxygens are there now?
12.
There are 12, so that's going to be -24 is the contribution from all those oxygens. In other words, if I lined up all the oxygens, each one, all 12 of them, have an oxidation number of -2, and so when I add up all the oxidation numbers, they're contributing a total of -24. How many sulfurs are there? There are 3, and they're each +6, so that's +18 comes from the sulfurs. So what must the contribution from the bismuth be? +6. So that this, because this is a neutral compound, so they have to add up to 0. In this case, I have 2 bismuth ions. So I'm going to take that +6 and I'm going to distribute it equally. So what is each bismuth going to be? +3. questions about that? Okay, let's do water. What's oxygen? -2, what's hydrogen? +1. What do we have here? What kind of compound is this? Ionic compound, sodium ions with what kind of ion? Sulfate. So if you can see a polyatomic ion and it hasn't changed, then that's an indication that it's not the thing that's getting oxidized or reduced, right? So I can just find my sulfates and say, oh, -2, +6, and sodium is +1. And if I want to be certain, I can double check by adding up underneath. So I've got -8 from the oxygens, +6, +2. And if those add up to my neutral compound, then I can feel pretty safe that that was, I didn't miss something. That makes any sense. All right, so now we have them all assigned. Let's figure out what's changing. So what's one of the elements that's changing? Manganese. So manganese is going from +2 to +7. Is that being oxidized or reduced? Is it gaining electrons or losing electrons? It's losing, it's becoming more positive. And I still do this. Loses electrons, I write the loses electrons, and then I say, oh, I know what loses electrons is, that's oxidation. It's very easy, because oxidation and reduction in their definitions are not things that you have fully incorporated into your worldview yet, but loss of electrons and gaining of electrons, I find, is something that comes more easily, because you've been thinking about charges and protons and electrons for 13 weeks now.
Can somebody just make up all these rules? Like, how do you know that there's +6 and -2 and +5 and all this stuff?
Can I answer that question after we finish this?
Yeah, I just don't believe you right now.
You don't believe that this is, oh. I'll come back to that question, but let's finish the analysis before because that will feel like a tangent, I think. So, what else is changing? So the manganese is losing electron. Oh, how many is each manganese losing? Each manganese loses 5 electrons. And I will tell you, I was doing this problem this afternoon in the airport, and I was trying to keep track of this without writing it down, and I got myself confused. Write it down, right? Because you can look at it and say, oh yeah, that's 5 electrons. And then by the time you've gone and done some other part of the problem, you will have forced that 5 electron piece of information out of your short-term memory. So write it down. Okay, so what else is changing? The Bi, the bismuth. So bismuth is going from +5 to +3. Is it gaining or losing electrons? It is gaining. Now, one of the things that happens is if you have misassigned your oxidation numbers, I've seen this happen, I've done it myself, you can end up with 2 things that appear to be gaining, and then you know you have a problem, right? If your numbers come out in such a way that one thing is gaining and another thing is gaining and nothing is losing, or vice versa, that's a problem. So, we're going to say each bismuth gains how many? So you go from +5 to +3, how many electrons are you gaining? 2 electrons. Okay, and so this is being used. Okay, now, how many total manganese are there in this reaction? There are 4. So 4 manganese times 5 electrons each. How many total electrons are being lost? 20 electrons lost. How many bismuth are in this reaction? There are 10. So that we've got this 10 coefficient out in front here, and here we've got a coefficient of 5, but we've got 2 bismuth. And because you should have the same number on both the reactant side and the product side, you don't have to count both, but you can double check yourself by looking at both sides of the equation. Is one way to kind of make sure you don't make an error. So we've got 10 bismuth, 1 whoops, that doesn't look like an I at all, times, what did we say, 2 electrons per bismuth, so that's gonna be 20 electrons gained. Questions about that? All right, now I'll answer Amy's question. So, the word oxidation came from scientists, we knew about oxidation and reduction before we knew about atoms, electrons, and protons. So, the word oxidation came from reactions that scientists were studying where what happened is you would start with, say, just some chlorine all by itself, and you would add oxygens in. Now, it turns out, if I could show you reactions where you would be seeing the chlorine losing electrons, which is what oxidation is. But they could count by mass. They knew that there was more oxygen getting incorporated into say chlorine, right? So it was going from Cl by itself to ClO, ClO2, ClO3, ClO4. And so they knew more oxygen was getting incorporated, so they called it oxidation. They had no idea about electrons. The original terms had nothing to do with gaining or losing electrons. The other thing that scientists were able to measure is that things were changing charge. So they were able, for example, they didn't know what the charges were, but what they were actually studying were things like this, where you're going from iron to iron 3 plus, right? So they were studying this. They wouldn't have written it this way because they didn't know. But they knew that if they went the other direction, that the charge, so they knew there was something about charge. The charge was being reduced, right? Same thing if they were studying this reaction. So they called that process reduction because the charge on the atoms they were studying, which they didn't know they were atoms yet, but they could tell that there was something happening with charge, and it was getting smaller, so they called it reduction. It was only much later, when we started to understand what was happening on the atomic scale, that we realized, oh, these things are actually connected to one another. This whole thing that scientists were studying that was oxidation, and this other thing that they were studying that was reduction, was actually transfers of electrons. And so the rules that we've come up with are rules to make it simpler for us to identify what's going on. So that's the answer to your question. They're not arbitrary, but they might seem like it when you first get started. All right, what else? Nicole?
Can you possibly post the application questions from this activity? 'Cause
They're not posted?
No.
Oh! Okay, sorry, somebody should have emailed me about that, because they're done. They were done last Wednesday, I thought I had posted them.
Darn.
Yeah.
That's okay.
Yes, I will post them. Yep, absolutely.
Can you go over how to
Yeah. Okay, anything else about redox before we move on to redox?
When it says what state, is it the MN in that whatever, would you say it was, they only give you a compound master in chemistry, asks you, it's ClO minus, what state is this, the chlorine?
Right, they're asking, when they say oxidation state, they mean the same thing as oxidation number. It's
Okay.
just another term for the same thing. So if you're given, something that's like ClO4 minus, and they ask for the oxidation state of chlorine, they're really asking for the oxidation number of chlorine.
Okay.
Okay,
So,
yeah,
sorry.
no, that's fine.
When we had a bromine, the trifluoride?
Yes,
Okay. So, the bromine was actually +3, but naturally it's -1.
Unless it's combined with chlorine,
Yes.
yes.
Is that always going to be the case for, I guess for this particular reaction? Or, is there a way we can always figure out which ways they're going to be?
So I think the rule, because the rules are hierarchical, and because of the way that the exceptions are listed, so for example, let's go to rules. So rule 6, chlorine, bromine, and iodine in a compound with other elements are it's gonna be -1, except when it's with oxygen or fluorine. Right, so, and you'll have these rules, so you don't have to memorize the rules, but you have to know how to use them.
So the coefficients never affect the oxidation numbers, right?
Correct.
Okay, but they do affect how many electrons are
How many
lost in the.
total electrons? Yeah, yeah, exactly. Yeah. And that's something that once you get it, then, so let me do one other thing with oxidation numbers. So, and I don't know if Ian ended up doing this or not in class, we talked about it. But where oxidation numbers come from, we just do water. What's the oxidation number of oxygen? -2, what are the hydrogens? +1. Whoops, +1. Now, if you didn't have the rules, you actually could figure those assignments out. Because the way we assign oxidation numbers is essentially what we're saying is in a compound, if we have something like sodium, then the oxidation number is the charge, right? That's just, we're counting electrons and they're legitimately, sodium is down an electron, so we say it's +1. But here, nothing has a charge, right? This is a neutral compound. But if we said, let's give the electrons in the bonds to the atom that's more electronegative, which in this molecule is what? Oxygen. So we're going to take these 2 electrons and say, you know what, let's just give them to oxygen. And let's take these 2 and give them to oxygen. And we're not actually breaking the bonds, we're just assigning them to the oxygen. So if an oxygen atom had 8 valence electrons, what would its charge be? Look at a periodic table and ask yourself, what would the charge on an oxygen be if it had 8 valence electrons? -2. So it's just like an oxide ion. It would be like O2 minus. That's its oxidation number. Now, what is hydrogen if it has no electrons? So normally hydrogen would look like this, right? This would be a neutral hydrogen. If we take that electron away, what's its charge? Not +0, because it's 0 when it has 1 electron. What is it if it has no electrons? +1. So because we took, in this configuration, hydrogen has no electrons, right? Because we assigned them all to the oxygen. And that's where the oxidation number comes from, comes for the +1. And that's why when we're assigning oxidation numbers, the coefficients don't matter at all. Because the coefficients would just say, oh, we've got 2 waters or 4 waters or whatever, but it's the distribution of electrons in the molecule that determines the oxidation number. I used to teach this, but it takes a lot longer because you have to draw Lewis structure every time you want to assign an oxidation number. And so now I use the rules because it's faster, although maybe it's more confusing, I don't know. But now you've seen both. All right, so can we move on from redox? Okay, great. All right. So the question is, this is question 18 on last year's exam. And I'm just going to draw it, and then we're going to talk about each of the statements that are there. Okay, there are 4 black triangles. And there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. So let's talk through the options. The first thing is, this is a solution of C4, Cl12, sorry. And it says the triangles represent the carbon, and the circles represent the chlorine. True or false? I mean, could that be true? Or could you make an argument for why it would be not true. If I have C4Cl12, what kind of compound is this? It's molecular or covalent. What do covalent compounds do when you put them in solution? Do they dissociate or not dissociate? They do not dissociate. So this can't be C4Cl12 because what this suggests is that you put the molecule in and it completely came apart into its atoms and now they're like zooming around independently. And molecular compounds don't do that. They stick together. The covalent bonds hold them together in solution.
So it would be like these
It could still be dissolved. So in other words, whether it's dissolved or not has to do with is each molecule blanketed by water molecules and each molecule can move around. But this can't be a depiction of C4C12 because it makes it look like there's 4 independent carbons and 12 independent chlorines, which if this was a molecular compound, if this was held together by covalent bonds, it wouldn't come apart in that way.
So if they're covalent, they don't dissolve. Like
They
all
don't
the-
dissociate. They might dissolve, but they don't dissociate.
Is that even a real stuff?
Yeah.
Is that a real thing? Can you make C4Cl12?
Don't know. I'm not sure it is. I'd have to think about how to structure it to get C4C12. Yeah.
So what would this look like if it was the right diagram?
Oops, sorry, I did it backwards. Well, I'll just do this. What is it? 8, 10, 12. Right, they would look like they're bound together. If I thought it was going to be solid, I would draw at the bottom of the beaker. If I thought it was going to be dissolved, I would draw it kind of floating in the beaker. And you don't have a way to know by looking at something like that whether it would be dissolved or not. So if I were asking you to draw it, I would accept either solid or dissolved, but I wouldn't accept dissociated. Right? I don't want it to look like all the atoms have come apart.
So dissociate means like atoms coming apart.
Dissociation means that the component parts come apart. Now, that doesn't mean every atom comes apart.
What does that mean? When you say that? The atom part.
Like each atom is separate, like atom.
Oh, like the C's individual and the C. Okay.
Right. Okay, so the second option is this is a solution of magnesium chloride. And the triangles are magnesium ions. And the circles are chloride ions.
It's 1 to 2, that doesn't make sense.
Okay, so the compound tells us that when this goes into solution, we're going to have one magnesium for every 2 chlorides. And so without doing any further analysis, we don't even have to figure out what the charges are or whatever. We don't have the right ratio of particles here. You can't put some magnesium ions in without also putting chlorides in. Okay? So it doesn't have the right ratio. But let's talk about, because we're here, we can talk about this. What kind of compound is magnesium chloride?
Ionic.
It's ionic. Is it soluble or insoluble?
Soluble.
Go to the solubility rules, look it up.
It says that it would be soluble.
Okay, and read the rule that you're reading to decide that it's soluble.
It says all chlorides, bromides, and iodides are soluble in water, except those of silver, lead, and
Mercury.
mercury.
Okay, so this would be a soluble compound. So let's while we're here, let's talk about what this would look like, right? So it would dissolve, it's ionic. If an ionic compound dissolves, it automatically dissociates into its ions. So it comes apart into its component parts, into the ions. So what would I change about this to make this be a correct drawing for magnesium chloride? I'd have less circles. How many circles, let's say we're gonna keep the triangles the same, how many circles am I gonna want? You're gonna want 8, so I'd have to get rid of 1, 2, 3, 4 of them. This shows a dissociated ionic compound it's dissolved, right, it's soluble, and the ions are dissociated. Okay? So you have to think about the ratio of the ions, you have to think about whether it's dissolved, and you have to think about whether they're dissociated. Okay, so let me put my things back in so we can. Have the right number down? Okay, so the third thing is this is a solution of iron hydroxide, and the triangles are iron 3 ions, and the circles are hydroxide. What kind of compound is iron hydroxide? It's ionic. How do you know it's ionic? Iron's a metal, looks like we've got some non-metals, okay? Could this be a good picture of that? Why not? Let me come back to Andy for a minute. Ian, why is it not? What was your reason?
Number 6 says all oxides and hydroxides are insoluble in water.
Okay, so as a hydroxide, unless it's like sodium hydroxide, potassium hydroxide, lithium hydroxide, right, unless it's rule number 1, this should look like what? It should look like a solid at the bottom of the beaker, okay? It should look like, is the ratio right? 1 to 3? Yeah, the ratio's right. So, but instead we would want it to look like this. Expect it to be a precipitate, a solid at the bottom of the beaker. Yeah.
It says that the iron are the triangles. So if we have a +3 and 4, but then you have 12 OHs. What's the charge of OH? If you have,
what is the charge of OH? It's based on the formula.
I thought they 3.
Well, we have 3 OHs, so each OH must be what?
Oh, okay.
Each OH must be -1
Okay.
to balance out the iron 3+. So you don't have to know, you didn't have to know that hydroxide was -1 in order to figure out that it was -1. Everybody good with that one? Okay, so far we've got 3 wrong answers. The molarity of the circles is 4 times greater than the molarity of the triangles. Yes or no? Hello.
It's not the right ratio again.
Okay, so what could we do to make this phrase true? 3 times. So if you weren't sure, like if this was too abstract, one of the things you could say is, oh, let me imagine that each one of these shapes is a mole, and that this is a liter, right? We would say, oh, okay, I've got 4 moles of triangles per liter. And then how many moles of circles do I have? I have 12 moles of circles per liter. And is that 4 times that? so you can make it concrete if you need to feel like, okay, I have to have a number that I can look at. All right, so that leaves the last option, must be the correct one, because we've eliminated all the other ones. It says, this is an electrolyte. The triangles and circles represent ions. So obviously we know that's true now because we eliminated all the other ones. But why is that true?
Because they would have dissociated or.
So if they were ions in solution, they would be dissociated, and when they do, then they will conduct electricity. So it's electrolyte. Any questions about this? That's a hard problem. There's a lot of thinking you have to do to solve that problem.
Would you go over 17? I think I know what you did, but just it looks a little confusing.
17 on last year's exam? Or
Yeah.
17, okay, yep. And did everybody find the ones that you know, that were on, last year they were on exam 2, right? There's some problems that were on last year's exam 2 that are on this year's exam. That's all. Let me answer this question first. So 17? Okay, 17 says a solution is prepared by adding 1.5 grams of solid sodium chloride to 50 milliliters of 0.100 molar. Oh, this is such a good problem. I have forgotten this problem. 0.1 molar calcium chloride. What is the molarity of the chloride ion in the final solution? Assume that the volume of the final solution is 50 milliliters. So assume that when we added this mass, we didn't affect the volume. Right? We just added some mass in and it dissolved and didn't change the volume. And we're told that the molar mass of sodium chloride is 58.44 grams per mole. Okay, so what is molarity? What's the definition of molarity? Moles over liters. So if we want the molarity of chloride, where we're headed is we want the moles of chloride per liter of solution. Do we know the volume of the solution?
Yeah.
Yeah, what is the volume of the solution? 50 milliliters. So we know this. I'm just going to change it to liters. What we need to put in is how many moles of chloride are in there. If we can put the moles of chloride in and divide by our volume, then we'll get the molarity.
No, she did.
This is liters. It's 50 milliliters, but I converted it to liters.
She thought you wrote 58.
What was that?
It's
that,
just,
that was like an 8.
there we go. Okay, so everybody clear that this is where we're headed. We need to figure out how many moles of chloride are now in our 50 milliliters. Okay, so our chlorides come from two places. What are the two sources of chloride? What's one of them? NaCl, so some of it's going to come from sodium chloride, and what's the other source of the chloride? Calcium chloride. So let's do one at a time. So, and what we're really going to say is how many moles come from, let's start with sodium chloride, and then we'll do, what was the calcium chloride? So we know the mass of sodium chloride. Can we figure out how many moles of chloride there are, or how many moles of sodium chloride there are?
Yeah.
What do? We start with the mass, 1.50 grams sodium chloride. How do I get to moles?
Use the molar mass.
Okay, I'm gonna use the molar mass. What goes on the bottom?
Molar mass.
Molar mass 58.44 grams per mole of NaCl. That's gonna give me the moles of sodium chloride. How do I get to moles of chloride?
Same thing.
It's gonna be the same thing. But if you want a conversion factor, you can say there is 1 mole of chloride in every 1 mole of sodium chloride. So that's gonna give us some number. I'm gonna call it X. It's gonna be X moles of Cl minus. So by dumping this mass of sodium chloride into our beaker, we have just dumped in X moles of chloride, whatever that number is.
I think what confused me is like the 1/1, that makes sense to how you got to chloride, but on the worked example, you didn't do the 1/1. So it looks like you just did,
Magic.
yeah, literally.
Okay, so let's figure out how many moles of chloride come from the calcium chloride. So in this case, we know we're starting with, before we put the sodium chloride in, this was 50 milliliters of 0.1 moles per liter calcium chloride. So how many moles of chloride were already in there? We know the molarity and we know the volume, so we should be able to get the moles of calcium chloride. So the molarity is 0.100 moles of calcium chloride per liter. And we know we've got how many liters? 0.05. That's going to give us moles of calcium chloride. But we need moles of chloride. What do we do to get moles of chloride?
2-to-1 ratio.
So we're going to do 2-to-1 ratio. Put these in parentheses so you can see that. So we know that there are 2 moles of chloride for every 1 mole of calcium chloride. So that's going to give us another number. I'm going to call it Y, moles of chloride. So just so you have a visual, before we added the sodium chloride, calcium chloride is soluble. Make sure I have the ratio. 1, 2, 3. We had a solution that looked something like this. And it had in it Y moles of chloride already. And then we dumped in the sodium chloride, and that added X moles of chloride. So our molarity then is going to be Y plus X moles of chloride divided by our volume.
Have we had to write out the balanced equation to find out like the two for one?
No, because this doesn't come from an equation, it just comes from the formula. So just by looking at calcium chloride,
Oh, you can see, okay.
we can see that there are 2 moles of chloride for every 1 mole of calcium chloride. Luke?
I'm confused with the calcium chloride part because isn't it like the molarity of the calcium chloride 0.1?
Yeah,
But we wrote it out as like the moles of calcium chloride.
right.
So anytime you see big M by itself is not a unit. You can't cancel big M. Occasionally you can, but mostly you can't. You need to rewrite it as moles of whatever that stuff is per liter. That's what molarity is. By definition, if I say it's 0.5 molar, I mean it's 0.5 moles of that thing per liter. That's what molarity is. It breaks out, it's a combined unit of moles per liter. And the reason I say if you see a big M, just rewrite it as moles per liter. Because it's the only way you're going to see the units cancel, right? So this only cancels because I rewrote molarity as moles per liter. Does that help?
Wouldn't you write it out as like 0.1 equals M over liters? Or
Right, so in this case, I wasn't given mole and volume, I was given the molarity. And the molarity by definition is the number of moles in 1 liter. So let me do a different example that might counterbalance it, but let me just make sure that there are no other questions about this, what we've done so far on this problem, and then I'll. Okay, so if I were to say, I have a sample that is 0.4 moles of MgCl2, and it happens to be in a volume of a half a liter, right? And I want to know what is the concentration. In that case, I would say molarity is equal to the number of moles over the number of liters, and I would take my 0.4 moles of MgCl2 divided by my 0.500 liters, and that's going to give me 0.8 moles MgCl2 per 1 liter, or 0.8 molar MgCl2. So I think that's what you have in your head, where you're taking moles and you're dividing by a volume. But if you're given molarity, basically what that says is, I don't even know what volume I actually have. I just know that if I had a liter, I have 0.8 moles. So if I give you a molarity, it's like saying this. 0.8 molar means there's 0.8 for every 1 liter. 0.8 moles for every 1 liter. And so if you're given molarity, I suggest you break it out so you can see that it's the per 1 liter. Does that help at all, Luke?
Yeah, that helps, thanks.
All right. There was some other question on a test, I think, that we were going to go back and finish this one. We did. I mean, we didn't finish the calculation, but basically we figured out how to get the moles of chloride that came from sodium chloride, the moles of chloride that came from the calcium chloride, and if we take the moles of each and add them together and divide it by the total volume that we've got, and then essentially we're doing this calculation again, right? We have a moles, we have a volume, and we're going to figure out the new molarity. All right, I'm going to erase this while somebody figures out the question that they have. Are there no questions about valence bond here? I'm a little worried there have been no questions about valence bond here.
I can't remember when I got started.
Yeah,
Oh,
could
is
you
that-
find some sort of hybridization problem to do, maybe?
Yes.
Drawing it out.
Indeed, we can. So the Monday before the last exam, we did balancing equations, then we did valence bond theory, then we did stoichiometry, then we did limiting reagents, then we did the different kinds of reactions in solution.
So next
And,
one's
and
like
molarity.
7A to 9D.
Yes, all of the chapter 7 activities, all the chapter 8 activities, all the chapter 9 activities.
Okay, so 7 through 9.
7 through 9. All right, so we're going to do something with hybrid orbitals, right? Okay. All right, so suppose I gave you this compound formula. And I want to know what kind of hybrid orbitals does the carbon use? What do you need to know to figure out, so look at page 141, you have your book. What is it that you need to know in order to assign the hybridization of an atom?
Is it like how many bonds it has?
How many bonds it has. So that means we're gonna need to draw a Lewis structure, okay? And I'm just gonna do that for you, because I know you can draw the Lewis structure if we have time. Okay, so now you've got a Lewis structure. Can you tell me what the hybridization of the carbon is? sp3. How do we know it's sp3? Because it has 4 regions. Is that the same rationale you were?
Yeah, it's just one less than
Yeah, a good mnemonic, right? So the number of P's is going to be 1 less than the number of bonding regions.
So I just count SP. I put 1 as SP, then I say 1, 2, 3.
Okay, yeah, that mnemonic works for sure. Okay, so this carbon is sp3 hybridized. What does a set of sp3 hybrid orbitals look like? What geometry do they have? They are tetrahedral. So if this is my carbon, so the first question was, what is the hybridization? That's the general gist of how you get there, right? Now if I said draw it, or pick from among these drawings, what's the right drawing? So the set, how many orbitals are there in a set of sp3s? So if I have sp3 orbitals, how many do I have? I have 4, and they're in tetrahedral geometry. So if I draw just their large lobes, it's going to look something like that. Basically what carbon has done is carbon started off with an s orbital and 3 different p orbitals. Think about these as if they were made of Play-Doh. They're not made of Play-Doh, right? But imagine that these regions of space were made of Play-Doh and the carbon came along and said, you know what? I need these regions of electron density to have a different shape, because I have to form some bonds, and these orbitals are not oriented in a way that's going to help me form the bonds. So I'm going to remodel them, and this is what I'm going to make. And so I'm going to make an sp3, an sp3, an sp3, and an sp3. How many valence electrons does a carbon atom have? 4. If it wants to, how many bonds does carbon need to form? 4. That means it's got to have 4 orbitals that are half filled, because in valence bond theory, the way a bond forms is you take one orbital that is half filled with electrons, and another orbital that's half filled with electrons, and you overlap them in some way. So if it needs to form 4 bonds, that means each of these orbitals has got to have an electron in it. Okay, so I'm just going to draw a big dot to represent, those are the 4 valence electrons of carbon. So hydrogen is going to come in. How many valence electrons does hydrogen have? 1. And what kind of orbital is that 1 electron in a hydrogen atom? It's an s. So in 2 of these positions, we're going to bring a hydrogen s in. We know what shape an s orbital, it's spherical. I'm going to put the other one back here, but it doesn't matter because all of the positions of the tetrahedron are equivalent. Now, chlorine. Chlorine has whatever its noble gas core is, which is neon. Is that true? Yes. 3s2, 3p5. Right. So if these were the p orbitals of chlorine, this one would be filled. This one would be filled, and that one would be half filled. This is the 3p5. find that? Does that kind of connect with what you remember about electron configurations? So one of its orbitals is half filled, which means it can do some bonding. So we've got two chlorines here. They're each going to bring a p orbital, the one that happened to be half filled. And I'm just going to draw it in a different color. So this is chlorine, and it brings its p orbital that's half filled. Here's the other chlorine, and it brings its p orbital that's half filled. We're not, in this particular drawing, we're not showing the lone pair electrons of chlorine, we're just showing the bonding pairs. We've got 2, 4, 6, 8 electrons that are being shared that are shown in this picture. What kind of bonds did we form? Sigma or pi? Sigma. How do we know they're sigma? Okay, so pi bonds are made from p orbitals. We don't have any p orbitals. What's another way we know these are sigmas? Right, so they're straight. So the overlap is along the bond axis. So if you drew a line between the two atoms, what's one other way we could know that these should be sigma bonds? So if I hadn't drawn this and I just showed you this and I said, how many sigma bonds are in this molecule? What's a single bond in a Lewis structure? Well, it's one, I know, but what kind of bond is it? Always sigma. So you don't even need to draw that. I mean, you have to be able to draw it. But to answer the question of how many sigma bonds are there, you just need to count up how many single bonds there are. Right? If there's 4 single bonds, you've got 4 sigma bonds. Now, in the entire world of molecules, there's a few exceptions to that, but not ones that you're going to see. A single bond is going to be a sigma bond. So if you're not sure how to draw it, and you're drawing single bonds, you just draw something that looks like it's along the axis, and you're going to be close, at least. Okay. All right, let's do another one. I had a question about that. All right, let's do another one. I'm just going to give you the Lewis structure. All right, so let's take one carbon at a time. Let's take the left carbon. We'll call that carbon 1. And the other one carbon 2. What is the hybridization of carbon 1? sp2. So carbon 1 is sp2. I'm just going to label it for now. Carbon 1 is sp2. What about carbon 2? Also sp2. How many sigma bonds are there in this molecule? Okay, we know there's at least 4 because there are 4 single bonds. I'll buy that. What's a double bond made of? 1 sigma and 1 pi. So how many total sigma bonds are there in this molecule? 5. So the first bond that's formed is always a sigma bond, and then if there's a double bond, the next one is a pi. If there's a triple bond, that last one is also a pi. So triple bonds are 1 sigma and 2 pi's. Okay? All right, so let's draw it. When you make sp2 hybrid orbitals, how many are in the set? 3. So if you don't have this handy, you're going to want to memorize table 1 on page 141. And then you're going to want to learn how to draw it. So if I take carbon 1, the set of, what's the geometry of the set of sp2 hybrid orbitals? Trigonal planar. So I'm going to draw them so that they're coming out of the plane of the paper. So this is an sp2, sp2, sp2. If we have sp2s, how many p orbitals did not get used? because we always start with a set of 3 P's, and if we've used 2 of them, that's what the 2 means, then we've got 1 left. So I'm going to draw the P orbital, and I'm going to draw it in a different color. So that's the P orbital. How many bonds does carbon need to form? What'd you say? 4 total bonds. How many valence electrons does carbon have? 4. So it's going to have to put 1 electron in each of these orbitals so that each orbital can be involved in a bond. Find that? So we're going to put 1 out here, 1 out here, 1 out here. Now, we're going to draw the second carbon. The second carbon is going to look exactly the same, just be the mirror image. Okay? So I'm going to do carbon 2 over here. Here's its sp2. Of the valence electrons, and then, oh, I didn't put the electron in the p orbital. Let's do that. Okay, so each carbon has 3 hybrid orbitals, 1, 2, 3, plus a p orbital, and each of those orbitals has a valence electron in it. What have I drawn here? It's a sigma bond. How do I know it's a sigma bond? So it's I haven't made it out of p orbitals, right? And how else do I know it's a sigma bond? It's straight along the line between the 2 nuclei, which is called the internuclear axis. Okay? So this is a sigma bond. So we've essentially drawn that bond right now. What can my 2 p orbitals do? They're lined up parallel to one another. What can they do? They can overlap side to side, on the top and on the bottom. So I'm going to draw these and say, oops, this region, and it looks like they're really far away, but in real life they would be much closer, and they kind of bend, the regions kind of morph toward each other. Now it looks like there's 2 bonds, but this is really only 1 bond, because it just has 2 spots where it overlaps. And this is the pi bond. Because it's not along the line that you would draw between the 2 carbons. So now we've drawn that bond. So that double bond is a combination of a sigma bond and a pi bond. What do we need to do to draw these 2 bonds? What do I need to bring in here? The s orbitals of what atom? Of the hydrogen. So I'm going to bring my hydrogen and my hydrogen. So now I've drawn this bond and this bond. What kind of bonds are those? They're sigmas. And notice that the overlap is if I were to draw a line between the 2 nuclei, the overlap's in the right spot. What do I need to bring in from the chlorines? Remember what we did for the first example? What did we bring in for the chlorines bond? P orbital, that half occupied p orbital. So I'm going to draw 1 here. This is chlorine. There. What kind of bonds are these? They're sigma. Right? If I draw a line between the nucleus and the other nucleus, the overlap is on that line. So now we've drawn those 2.
It looks like you made 2 pi bonds on the bond.
I know, it looks like it, but a pi bond, a single pi bond looks like that. A single pi bond has 2 regions where it overlaps.
Okay.
Luke?
I don't get why the chloride's like a P and a P orbital and the hydrogen's.
Okay, so the valence, it's a great question. What valence bond theory says is that an atom like carbon will reorganize its electron density if it has to in order to form a bond. Remember that chlorine, its electron configuration, which is just an atom all floating by itself, is 3s2, 3p5. And we could say, all right, here's its s, it's got 2 electrons in it, and here is its set of p's. Oops. Okay, and this one has 2 electrons in it. Let's say this one has 1, and this one has 2. It doesn't really matter which one is which, because the atom, they're 90 degrees from one another, and the atom can rotate itself wherever it wants to get. But one of them is half filled. And this is the one that can come in, bring 1 electron, and form a bond. The rest of them are still there, we're just not drawing them. Does that help? So the way that valence bond theory would describe this molecule is it would say these 6 electrons are right there. And then this orbital is going to come in and form the bond with the hybrid orbital of carbon. Should we do one more? Or should we move on to something different?
So are there, there's 5 sigma and 1 pi for that then?
There are 5 sigma and 1 pi. Yep.
So we had another carbon, or if we do H2CCCH2.
Uh-huh.
I think this was on the application question.
Yep.
So we had 3 carbons, and the question was, are all the H's on the same plane?
Yes. Yes. So let's first change this problem to hydrogens for a minute. Do you mind that if I just change that to hydrogens? So are these 4 hydrogens in the same plane? So if I am C2 and my hydrogens are out here, my p orbital standing straight up and down. And now I'm C1, my hydrogens are out here and my p orbital standing up and down. My hydrogens all in the same plane, right? And if I were to rotate, so now think about my head as the p orbital. If I were to rotate this way, can I form the pi bond? Right? If this one stays upright and this one rotates, can I form the pi bond?
No.
No. So the pi bonds the p orbitals have to be parallel to one another to form the pi bond, right? So right now the p orbitals are like this, and that puts these hydrogens like this, and these hydrogens like this. I feel like a cheerleader, right? But if I did this, if I rotated it, now the pi bond would break, and then I wouldn't actually be sharing the right number of electrons. So the pi bond, actually one of the things about pi bonds is they make molecules rigid, because if you just have a sigma bond, everything can rotate and the overlap can still happen. But when you have a pi bond, you can't rotate anything or you're going to break the bond. So the base pairs of DNA are flat and rigid because they've got a bunch of pi bonds on them. Okay, so now let's go to Susanna's question, which is, her question is this. We have this molecule. Now the question is, are these hydrogens all in the same plane? What's the hybridization of this carbon? sp2, align that. What about this one on the right? sp2. What about the one in the middle? sp. So 2 regions, we just need 2 hybrid orbitals, so this is going to be sp. So let's start by drawing that middle carbon. So we'll call this carbon 1, carbon 2, carbon 3. Let's start by drawing carbon 2. So if I have 2 hybrid orbitals, what is their geometry? So if I have sp, okay, let me go back one step. If I have sp orbitals, how many come in a set? 2. And what is their geometry? They're linear. So they're going to be sticking out from my central carbon. So here's my C2, and one of them goes like this, and one of them goes like this. How many p orbitals have we not used on the carbon? Remember, we always start with 3, and if we've used one of them, then we've got 2 left, so let's draw them. One is going to be in the plane of the board, and the other one is going to be coming out of the plane of the board. How many valence electrons in carbon? 4. How many bonds does this carbon have to form? 4. I'll come back in a minute. So each one of these orbitals is going to have an electron in it. Because if we need to form 4 bonds, then this orbital is going to have to form a bond, this orbital is going to have to form a bond, this one's going to form a bond, and this one's going to form a bond. One of the things that can be confusing is this is an orbital all by itself. It can potentially fit 2 electrons. This is an orbital all by itself. It can fit 2 electrons. So each one of these big lobes is an orbital, and each orbital can fit 2 electrons. This thing and this thing is a p orbital, and a p orbital is one orbital with 2 lobes. So this whole thing can fit 2 electrons. We can't do 2 up here and 2 down there. Does that make sense? So hybrid orbitals are fundamentally different because they just have one big lobe on one side, and there's a little bitty lobe that we don't usually draw because it just makes the drawings even more confusing than they are. Okay. All right. So let's go back and ask how many sigma bonds are going to be in this molecule. 6. Let me see if I agree with you. 1, 2, 3, 4, 5, 6. I'll buy that. How many pi bonds? 2 pi bonds. Okay? So let's make sure we draw 6 sigma bonds and 2 pi bonds. So the carbon 1 is going to look just like this carbon over here, right? So it's a carbon bonding to 2 hydrogens and a carbon. So all I need to do is take this piece and redraw it. Let me just show you. I'm going to take this part of this molecule and draw it over there because that carbon is doing the same thing. So I've got carbon, here's its sp2. sp2, sp2. I'm going to erase this so that my molecules don't run into one another. And I'm going to put hydrogens out here. What else goes on this carbon? A P, right? So I need to draw its extra P. It's going to have an electron in that P and an electron in this hybrid, and then one in each of those. What can these 2 p orbitals that are now lined up parallel to one another, what can they do? They can pi bond. And remember that they're going to have 2 regions, so it's going to look like there's 2 bonds, but there's only one. Okay, how many bonds have we drawn so far, total? How many bonds have we drawn? How many total bonds have we drawn? So I count 1 sigma, 2 sigma, 3 sigma, and then a pi. So 4 total so far. Okay, all right. So this carbon is going to be the mirror image of carbon 1. Buying that? Right? Because it looks just the same way but on the other side. But let's think about this for a minute. If I draw this, so let me back up. I am carbon 1. My p orbital is up and down. I'm carbon 2, I have 2 p orbitals, one that's up and down and one that's coming out of me. The one that's up and down is pi bonding over there to carbon 1. The one that's hanging out, ready to do something, is pointing out at you. Find that? So what do I need to do when I draw carbon 3? Where does its p orbital need to be? It needs to be pointing out so that it's parallel to this one that's hanging out ready to bond. So let me draw it, and then we'll do that again. I'm gonna need the p orbital on this carbon. Here's my carbon. I need the p orbital on this carbon to be parallel to this one that's coming out of the plate. And that means my set of sp2s is going to be in the plane of the paper. So it's like you're looking down on the trigonal planar, and this is coming out of you. So this is sp2, 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 hydrogen, hydrogen. Right, let me stop, I'll let you draw, and then I'm gonna act it out again, and then we'll finish drawing the bonds.
So that middle p orbital can't be used twice?
Correct. The middle p orbital can be used twice unless we're drawing a structure with resonance, and we're gonna spread out the electrons over even more atoms. But you can't double share out of this orbital. Okay, so carbon 1, my lone p orbital is here. Carbon 2, I have a p orbital here that's overlapping in a pi bond with the one on carbon 1. I have one sticking out here. And now, in carbon 3, it's got one p orbital and it's sticking out at you. So now we can do a pi bond side to side, but it's coming out at you. Okay, so let's draw it now. So it's going to be overlapping way back here in the back, and then up here in the front. Are the hydrogens all in one plane? They are not. So over here, remember my p orbital sticking up? My hydrogens are out here. So this p orbital is overlapping with this p orbital. Now I'm in the middle carbon. There's another p orbital. Now I'm going to come back over to carbon 3. I've got these p orbitals overlapping. In order for that to happen, then my sp2s have to be going like this. Right? So the hydrogens are in the plane of the board over here, but they're perpendicular to the board. They're in a plane that's perpendicular to the board over here.
Why does it look like there's two pi bonds? There's two p orbitals between the C's? There are.
Come point to what you're asking to make sure that I answer this question.
There are, okay, it's just as if there are two. Like, are these two separate p orbitals?
Yes.
And why does it have two?
Because this carbon is sp hybridized.
So it has 4 p's?
No, it started with 3, and it used one of them to make the SPs, and then it had 2 left.
So does when it bonds, does it like turn it or like twist it or something, and that's why the hydrogens aren't in the same plane?
Correct. Right. In order to allow this p orbital to overlap with this p orbital, then it's got to be in the hybrid orbitals have to be in that configuration. Yeah. Like,
So are sigma and pi bonds both covalent bonds?
yes. Sigma and pi bonds are both covalent bonds because they allow 2 different atoms to share electrons with one another.
And I'm guessing there's probably differences in how they actually function, but not how they're represented.
So they are, to give me a sense of what you're thinking about in terms of function.
Well, I'm assuming they push and pull electrons differently than
Yes.
the others.
Yes, so sigma and pi bonds are a little bit different. It's easier to break a pi bond than to break a sigma bond, because the overlap isn't as great. But if you have a pi bond, you never have a pi bond by itself, right? You always have a pi bond on top of a sigma bond, or 2 pi bonds on top of a sigma bond. And so, this is why breaking a double bond is harder to do than breaking a single bond. Because to break a double bond, you have to break this overlap and this overlap. Whereas a single bond, it's just, you know, two orbitals overlapping, it's much easier. Does that help at all? Or, I mean, does that paint the picture?
I think so, it's a little bit.
Yeah, so it turns out, so valence bond theory is only one bonding theory, and it's not the most sophisticated bonding theory, but we use it a lot because it is based on Lewis dot structures. It's pretty simple and it explains a lot of things. Turns out there's a lot of things you can explain based on the percentage of the orbital that is S character, right? So if you make an SP, that's 50% S, 50% P, right? But if you make an SP2, now it's only a third S and 2/3 P, right? And we know that S's and P's have different characters, so there's some things we can explain based on the differences of the total character in S and P. So there's some things we can do with it, but most chemists now, if they're, so you'll, like, for those of you who are going on to organic, you'll see this a lot. You'll need to know, how do I predict whether something is SP, SP2, SP3 hybridized? You'll need to be able to picture and describe sigma and pi bonding. You'll deal with these kind of pictures. But if we were trying to be doing something more sophisticated, we would use a totally different theory. Right? Scientists in general use the simplest theory that can be used to explain the thing that they want to explain. And it turns out valence bond theory explains a lot of things, so we use it. But if we really wanted to look at the functionality, we would probably look at a different theory. All right, we've got 20 minutes. Prove.
What's the difference between non-ionic equations and molecular equations?
Okay. Good question. All right, let's do this reaction. Okay, so suppose I said, here you've got two beakers. One has, do you know what the name of this acid is? This is sulfuric acid. So one beaker has sulfuric acid in it. The other one has this. Do you know what this one is? You might not know because I didn't make you memorize the name of this ion.
Lithium hydroxide.
It's lithium hydroxide. So we've got one beaker with sulfuric acid, one with lithium hydroxide. I want to know when we dump them together what reaction is going to happen. And I want it in its complete molecular form, its complete ionic form, and its net ionic form. Okay, so I'll just write that over here. Molecular, complete ionic, and net ionic. Now, different people have different strategies for solving these kinds of problems. But what I think is helpful when you are new to this is that you start by thinking about the complete ionic. And by that I mean you take these things, which are really chemistry shorthands for what's going on in the beaker, and you rewrite it to represent what's really happening in the beaker. And that is that this is a strong acid. What's true of strong acids in solution?
Conduct electricity.
They conduct electricity. What about their ions? They dissociate. So this is really going to be 2H plus sulfate in solution. Now it turns out it's a little bit of an oversimplification for this acid, but for our purposes this totally works. This is dissolved, and we can tell it's dissolved because it's got AQ after it, right? So it's an ionic compound. If an ionic compound dissolves, what does it do? It dissociates. So we would represent this as okay. So really, those are what our reactants are. So we've started. So this is the start. ionic form. Now, and the reason I like the complete ionic form is because it shows us what is there to possibly react. So when we start, this is in a beaker all by itself. And then this is in another beaker all by itself. When we combine them, we have some new possible combinations, right? We can take this cation and this anion, and this cation and that anion, and ask, would anything happen? Or would they all just stay in solution? If they all stay in solution, what do we call it? No reaction. But in this case, what would happen? Is there any combination that would do anything? Let's ask about lithium and sulfate. Anything happen with that? What would happen? You think it might form a solid. So I realized, and I posted this on Piazza because somebody asked a question, that the first solubility rule, and this is fixed on the test, the first solubility rule says all potassium and sodium salts and all ammonium salts are soluble. It should also say all lithium salts are soluble. It is a game changer. But I'll make sure you have the right rule for the test. So, without that rule, you would be right to predict that lithium sulfate might be insoluble. But in this particular case, all lithium salts are soluble. So lithium sulfate is not going to come out of solution. But that's exactly what you want to be looking for, is what are the possible combinations that might form a precipitate. What about H plus and OH minus? What does that form if you put them together? H2O. So one of our products is actually going to be a new compound that has covalent bonds. And then the lithium and the sulfate are just going to stay in solution. Now we have a problem here. Everybody know what the problem is?
No.
It's not balanced. So how might we balance this? What could we do to balance it? Great. So we want to change the coefficients, and in fact, we don't want to change anything but coefficients to balance it. What coefficients could we change so that we could balance it? Okay. So how many lithiums do you want?
Well, if we want to make Li and SO4 bond.
Okay.
2 of 1.
And so we don't necessarily want them to bond, but we do want them to cancel out each other's charge, for sure. Like we can't have only 1 plus and a 2 minus. That's not going to happen. So we could put a 2 here, but if we put a 2 here, we're going to need to put a 2 here. But lithium came with hydroxide. Right? We can't have 2 lithiums and only 1 hydroxide. So if we put a 2 there, we've got to put a 2 there also. And that tells us we've got to go back up here and put a 2 there. Do we need 2 on H2O?
Yeah.
We do. Indeed. So now, is it balanced for mass, meaning the right number of atoms on each side, and charge? Do you have a question? Yeah, go ahead.
So when it's like the molecular part on the top, will always be like the inner ones combined with the outer ones?
Potentially, right? That's what we want to look for. Right? We want to ask, is it possible that these can combine?
Okay.
Yeah. All right, so now we've got a balanced complete ionic form. What do I write as the phase of water? Okay. So let's go back now. Let's go backwards and write the complete ionic. The molecular. So I'm going to take my 2 waters. And then what am I going to write here? Do I write this, or do I write something different? We're going to put it together as though it were together in solution. Now, how do I write that?
Li2SO4.
Li2SO4. You buying that? And what do I put here? Aqueous. So this is chemist shorthand for this. So people who have learned how to interpret this notation can look at associated in solution because that's what it really is. It's just it's faster to write this.
How do you know like what's gonna bond with what, like, that hydrogen's gonna bond with the oxygen to?
Good question. So hydrogen will only bond with what's the charge on hydrogen? +1, so it's positive. And so it's only going to interact with things that are negative. Right? It's not going to interact with things that are positive, they're going to repel each other. So hydrogen can't interact with lithium. It was already in a solution with sulfate, and it wasn't interacting with sulfate. So the only other option is OH. We could do the same thing with sulfate. Sulfate came in, it was already combined with H+, and they weren't interacting. It's not going to combine with OH- because they're both negative. So lithium is its only other option.
So like, how do you know if it's gonna like, if they're gonna switch like that, or if they're just gonna stay the same?
Good question. Let me finish the net ionic and then let's go back to that. Ian, do you have a question?
I was just gonna say it's that you compare, or combining with the solubility rules, right?
Right. So let's just do the net ionic. How do we go from complete ionic to net ionic?
You use the
What do we take out?
spectator.
Spectator ions. So the spectator ions are the ions that, from their point of view, they started off in a beaker, blanketed by water molecules, just happy that there was something else in there to balance their charge. And when they got done, they were in that same state. They could care less what happened, right? And so in this case, that's going to be our sulfate and our lithium. And so we take those out, because when we take them out, that illustrates what the chemical changes occurred. What could we do to this to make it simpler?
Take out the twos.
You could just take out all the twos, right? But I would accept it like this. All right, should we do one more to get at Luke's question about how do you know what's going to happen? What I will say is, there's in your life, in this course, there's only two things that can happen. Three things. Nothing, right? No reaction. You can form water, and generally you're going to form water when you have an acid and a base. So you saw this in the lab, you did an acid-base titration. You titrated sodium hydroxide with hydrochloric acid, and that was HCl plus NaOH goes to water and NaCl. So the reaction of any acid and base is water plus another salt. So nothing can happen. You can form water, or you can form a precipitate. Those are your three options. So let's do one that forms a precipitate so we can look how that works. Oh, hold on, that's not what I want to do. Pick a different map. Okay. So I'll model a different way to solve these. This is how I actually do them. I do this more in my head. It's cool, but what I do is I say, okay, what have I got here? I've got sodium ions, I've got sulfide ions, I've got iron 2+ ions, and I've got nitrate ions. Notice that I haven't worried about how many of them I have, because it actually doesn't matter at this point. It will matter later, but it doesn't matter now. Sodium and sulfide came in together. They're already dissolved and dissociated from one another. So I don't have to worry about them, because I know that they're gonna stay dissociated, because that's how they came in. Same thing with iron and nitrate. I know those they were already in a beaker, dissolved and dissociated, they're not gonna interact with one another. So what is possible for sodium to interact with?
Nitrate.
Nitrate. Why? Positive and negative, opposite charge. Why not iron 2+?
Same charge.
They have the same charge. So really, my only option is sodium interacting with nitrate. So the question is, could that do anything? What about sulfide? So it's already come in with sodium. Is it going to interact with nitrate? Why not?
It's negative also.
Right, so they have the same charge. They're going to, if they bump into each other in solution, and they might, they're going to repel each other immediately. They're not going to stay anywhere near each other for any length of time. So that means that the only thing that sulfide can do, potentially, is interact with iron 2+. Right? So now I can say, all right, well, what are my possible things? Sodium interacting with nitrate. Right? I can write the formula. Right? That's a neutral combination of sodium and nitrate. Is it soluble or insoluble?
Soluble.
It's soluble. How do you know it's soluble?
It's a nitrate.
It's a nitrate and it's also a sodium salt. So all sodium salts are soluble, all nitrate salts are soluble. Okay, what's my other possibility? What's iron and sulfide? So that's going to be FeS. Again, notice I'm not at all worried about how many of these things I have. I'm just thinking about what are the possible combinations. Is this soluble?
Sulfides are insoluble.
Sulfides are insoluble. There's a list of exceptions. Is iron one of them? No. So this is going to be solid. Now, I can worry about how many I have. How many sodiums do I have on the left? And so how many do I need on the right?
2.
Does that take care of my reaction? Isn't that sweet? Right? Now I can go and I can write them complete ionic. Right? So my complete ionic is going to be 2 sodiums plus sulfide. It's going to be an iron plus 2 nitrates. I'm going to stop in a minute and just make sure that you're following how I'm doing that. Right? So this is kind of what I did as a first step before, which is saying, all right, I've got this stuff, let me just blow it all apart into its ions.
On the test, do you want us to write the charges?
Yes,
Okay.
absolutely. Because, first of all, they are charged, so we should represent them that way. Secondly, one of the ways you can discover an error is you can see, oh, wait a minute, I don't have the same number of positives and negatives, and if you've left the charges off, you can't see that.
Is this exam gonna be as long as the last one?
I have no idea, because it's not done yet.
Oh, okay. If you want us to like take a run through of it, and then
My goal last time was not for it to be as long as it was, so my goal is for it to be shorter.
okay.
But you can see that I don't always get it right, so my goal is for it to be shorter.
Okay.
Probably maybe a little bit longer than the first one, but closer to the first one than the last one, you know. But it's really hard for me to guess how long things are going to take you guys. So I got it wrong last time. So I'm going to maybe be a little more conservative this time in terms of my extrapolation to how long it's going to take you. All right, so here's our reactants. Now, we can take our products. How should I write this product? Separately. How do I write that? 2 Na pluses.
Do you have to use a coefficient, or could you do a subscript?
You have to do a coefficient.
Just because that's how it is in that equation?
Because the 2 tells us that there are 2 sodiums independent. If I write this,
Oh, then it looks like a compound of
If I write Na2, that tells me that the two sodiums are zooming around together.
Oh, okay.
So it actually means something different to have a coefficient versus a substrate. Okay, so I've got part of my compound written. What comes next? What, Harvard? Okay, and how do I write, so I've got NO3 minus, where do I put the 2? In front of it. Because this remember is shorthand, this is a chemist's shorthand for, we've got 2 sodiums zooming around and we've got 2 nitrates zooming around. Whoops, and this is aqueous. What do I do with this? We leave it as the combined compound because it's a precipitate at the bottom of the beaker.
How'd you find the FBS was a solid?
Because we looked at this, remember we were looking at this possible combination and asking the question, when we combine those, is that compound soluble or insoluble? So we looked at solubility of those.
So in the original, like Na2S, like it's a subscript, but then when you separate it down here, you put it in front.
Correct. Because when it started, because when we put Na2S in solution, so let me just imagine are the triangles and S, so this is S2 minus, and the 2 triangles are sodiums, right? In the solid, they're packed together next to each other. But as soon as you put it into solution, then they are zooming around totally independent of one another. And so we count them and we put the 2 in front.
So up there, that's them individually, and then this next equation is them once they're put into the solution.
Kind of. The problem with so no, this is shorthand. This means the same thing as this. It's just that you have to see, oh, it's an ionic compound, it's aqueous, and you have to imagine it as this. So at somewhere along the line it was this. Na2S solid, and then that got dumped into water. And this is it already in water, which is shorthand for this, which is annoying. But the shorthand, I mean, it's a pain to write out these complete ionic equations, right? You've got all these charges and blah, blah, so like once you get comfortable with them, this is way easier to write, which is why in chemistry everybody else. So, and then to get to the net ionic, what do?
You just do that.
Take that from the spectator. So one thing to watch for when you're doing these is make sure that in every version of your equation, everything's going to be neutral. So all of our reactants are neutral, all the products have to be neutral, right? Here, if you add up all the charges on the reactant side, they add up to 0. If you add up all the charges on the product side, they add up to 0. Right? So check for charge balance. Check to make sure I have 1 iron over here, I have 1 iron over here. If you're not able to balance it, then somewhere along the line you did something like you said, oh, iron 2 plus can combine with 1 NO3 minus. And you wrote that as though it was neutral, even though it wasn't. I actually, like once you get good at these, they're like little puzzles. Like, oh, how many can combine with whatever else? And then like 3 weeks from now, you'll be like, I don't even know how that was. But it is at first. All right, it's 6 o'clock.
For general, so a lot of the master chemistry would ask, like, when balancing equations, they say, like, sulfuric acid formed when gas and sulfuric dioxide reacts with whatever. Like, are you going to expect us to know how to, like, make those and then balance it?
No.
No.
So there are some, so I've written most of the test on the plain thing. So, actually, I wrote it half on the plain thing, half was written during the conference. There are questions on naming acids and molecular compounds, because those are the last 2 things that we've learned since the last exam, but they are not combined with a problem where I would say, sulfuric acid combined with blah, blah, blah. They're separate problems.
Were there videos on naming acids?
Yes. Yep. took the last few application questions and made a video out of these, so if you wanna go back over more of that, that's a good video on that.
I literally do nothing.
All right, thank you.
Cause I'm like, oh, like all the other homework.
Just say, can you look at my master chemistry and make sure that